Just set them right there, I think, because let's see. Do y'all care, really, about these? We went to y'all know where we went? Bogotita. We went to Bogotita State Park. Oh, but this is really cool. Did y'all ever do 100th day of school things, festivities? Yeah, so my little girl, I'm a 4-year-old girl, they had to make T-shirts, and so we get those iron-on deals that you can print on your computer and then just iron them onto her T-shirt. So she had a T-shirt that had this on it. You see, she's a 1, and then she's a 0, and she did this little back bend, like a 0. And that was my boy's. He made 100 out of 100 Legos, and we put that on his T-shirt. These are just the pictures. What number is that? That's a 1. That's a very serious one. That's not the one we used. We used that one. And that was a 0, but that didn't work very well, so we did the back bend. These. Oh, that's our dog. That was before the haircut, which he got just a week or so ago. Let's see, my girl, she got her fingernails painted. You see they have little decorations on them? My wife did that. It's pretty good. What's on that hand? Can y'all see? Yeah, they're little hearts. Let's see. So we went to Bogotita State Park. They have this really cool system of trails that goes down into the gorges, and you can go down there, and there's all sorts of neat things like down into the gorge. So these are the steps. You can sort of see the trail back in the background. It was raining like the entire weekend. Y'all remember over Mardi Gras? Yeah, it sucked, but we had a good time. That was the trail down in the gorge, or one of the trails. That's my wife. The big one. The little one's our little girl. This is the river, the Bogotita River. It was cold, but we still played. And then we came back, and we stayed in the cabins. The cabins in the state parks in Louisiana are superb. They're very nice. We liked it. We've been to a bunch of them. Let's see, we made a fort because it rained all day, so I think that's about it. What's that, David? Oh, yeah? See, we found this hole. I thought it was an armadillo or possum, maybe. My little girl wanted to crawl up into it and see if she could find it. It was a pretty big hole. All right. Oh, and there's our dog. He just got a haircut. All right. I think that's all. All right. So bring me your proposal. You can give it to me at the end of class if you like. I do need if you sent me an email, I emailed you back and said I needed a printed version, so those emails are long gone. So if you sent me an email, please bring me a paper copy because it's easier for grading. I have your quizzes from last week if you weren't here last time. Thank you. Caleb? Caleb? Oh. It's Caleb. All right. Yes, I am. Oh, so if you didn't get your quiz last time, just see me after class and I'll give you your quiz. And I'm not sure when the next quiz is. Anybody know right off? Next Thursday? Seriously? Okay, so it'll be not this Thursday, but next Thursday. It'll probably be 2 chapters again. The chapter on Newton's laws, which we're doing right now, chapter 3, and then chapter 4 is on work and energy. It might have a little bit of chapter 5, we'll see, but probably just 2 chapters. All right, we were talking about forces. We're sort of going through these different types of forces. There were gravitational forces. That's the force due to gravity. So when we talk about an object that has mass, that's sort of an intrinsic quality of an object, that it has mass. But then when we talk about weight, that's the effect of whatever planet they're on that mass. So for example, something that has a mass of 10 kilograms is going to have a 10 kilograms anywhere, be on the Earth or on the Moon or on Mars or whatever. But an object that weighs 700 newtons, that's particular to this planet. So something that weighs 700 newtons here might weigh less than that on the Moon, say 100 newtons or whatever on the Moon. So we talk about gravitational forces. sort of wrapped up in that with center of mass. Center of mass is the point in an object where the force of gravity is considered to act. Then also about the universal law of gravitation and why it's important to measure the acceleration due to gravity. And then the last couple of forces were the normal force. Somebody tell me what the normal force is? When do you encounter a normal force? You're encountering a normal force right now, right? What is it? What is it? Okay, it's Newton's third law. Newton's third law, remember, is that if I have one force, then I'm going to have an equal and opposite force. So the normal force that you're encountering is the normal force that's due to the gravitational force. So gravity's pulling you down, and then something is pushing you back up. What is that? The chair, right, Kelsey? So the chair is pushing you back up. That with a force that's equal and opposite to the gravitational force. We also talked about friction. That's sort of the last thing. We have two types of friction, kinetic friction and static friction. Some examples of kinetic friction. If I rub my hands together, the rotors on my car brakes, the brake pads and the rotors, when they engage, those rotors are spinning. Well, when it stops, it goes to what? What type of friction? Static. Did any of y'all do that little experiment? Did you? Did you notice the alert? Yeah, y'all try it out later today if you didn't. I know it's difficult to stop at stop signs, but you have to do it very slowly. All right. What's usually bigger, static or kinetic friction? What's a bigger force, static or kinetic friction? Yeah, static is a bigger force. And that's demonstrated, like if you're trying to push a piece of heavy furniture, that it's very difficult to get it moving at first, but then after you get it moving, it's a lot easier to keep it moving. Right? And that's because after you overcome the static frictional force, that kinetic frictional force is a lot smaller, quite a bit smaller in some cases actually. The amount of the friction, though, depends on the two surfaces that you're dealing with. And there's a table in your book, which I pointed out last time. I think it was on page 39, that gives those coefficients of friction for both static and kinetic friction for different materials, different types of materials. All right, let's look at an example. This is from your book. It's example 3.4. I have a person on wet snow and wooden skis. So a person on wooden skis is on wet snow. And it's important what type of skis, what the skis are made of, and what the snow is like. Because if you look on page 39 at that table, likely on the quiz next week, you'll have this table. I'll just photocopy it and put it on your quiz. If you want to know the coefficients of kinetic or static friction, you can just look there on page 39, and you'll just go down, and let's see, I see waxed wood on wet snow, and it gives both the kinetic and the static friction coefficients. All right, so in the homework, there are some examples to use this, but make sure that you're familiar with this and that you can just, you know how to read it and what the numbers mean. All right. So this person on wood skis is on wet snow. The person has a mass of 70 kilograms. And I want to know what is the maximum force that you can exert on this person without making her move. All right, so this is my person. She's on wooden skis on wet snow, and I'm going to push her with a certain force, and I want to know what that force is so that her velocity is equal to 0, so that she doesn't move. All right, in this case, since her velocity is 0, her acceleration is also going to be 0. So I want to know what force I can push on her with so that she doesn't move. Now that force is going to be equal to what force? Imagine I'm pushing this piece of furniture, right? If I push the piece of furniture and it's not moving, what is the force that I'm pushing on it with? No, let me draw a picture. I'm not sure I'm making myself clear. This is sort of a little aside. Let's say that I have this piece of furniture. It's not moving. It has zero acceleration, right? And I know from Newton's second law that F is equal to ma, all right? Let's see, we talked about net forces. I'm not sure that we have. Let me go back and look. Give me just a moment. Okay. We said from Newton's second law that F is equal to ma. I'm going to say this in particular, that the net force is equal to the mass times the acceleration. All right, we're going to come back to the problem, but let me just have this little aside. When I say that the net force is equal to the mass times acceleration, that means that the sum of all the forces is equal to the mass times the acceleration. So for example here, let's say that I have one force that I'm pushing on this piece of furniture. It's a couch or whatever. I'm pushing on this piece of furniture with a certain force. And then there's going to be another force that's in this direction. And this is going to be my static frictional force. All right, so this object isn't moving. It's like I have this furniture here. I'm pushing on it in this direction. That's the blue arrow. And then the static frictional force is going to oppose that force. And the static frictional force in this case will equal the force that I'm pushing on it with. What would happen if the static frictional force was bigger than that force? What would happen to the chair? What, Kyle? No, it wouldn't stay still. It would go that way, right? Rhiannon, is it? No. Huh? Okay, I'm sorry. Can you say it again? Terrion. Where's Rhiannon? You're Rhiannon. Okay. All right. Yeah, so if the static frictional force was bigger, then it would move to the left. But that never really happens, right? The static frictional force is never going to exceed the force that you're pushing on it with. All right? So when I talk about net force, for this case, the net force is really just the sum of the two forces. So in this case, the net force is going to equal the force that I'm pushing on it with, minus the static frictional force. And if it's not moving, as this is the case, this is going to equal mass times acceleration, and that's going to equal 0. We'll get into this a little bit more in just a moment. We'll do a little bit of stuff with vectors. All right? Huh? If it's not moving, yeah, your net force is going to equal 0. All right, well, we'll see some cases where it is moving, in which case your net force is non-zero, something greater than 0. Yeah, David? Right. Your net force in general is just the sum of all the forces. Okay. We're going to get into this with vectors. Let me just give you a quick explanation. In this right-handed world that we live in, we live in a right-handed coordinate system. We always take right to be positive, and we take left to be negative. So it's just a convention that we take, that right is always positive and left is always negative. Okay, so right, the sum of the forces, the one that points to the right is going to be positive, and the one that points to the left is negative. And that's because, I mean, it's just something that we impose on the world, that we have a right-handed coordinate system. You ever heard that term, right-handed coordinate system? It comes from this, like this is the coordinate system. It's right hand. Y'all know that? Do you care? No, that's okay. But you live in it, right? We'll come back to vectors. We're going to do some simple vector stuff in just a bit. All right, so back to this problem. I have this person on the wooden skis here. If I'm pushing on this person with a certain force to the right, is there another force that's pushing back on that person if she's not moving? And what is that force? It's the static frictional force, right. So I'm pushing her in this direction, and so there's an equal and opposite force that's pushing in the other direction. All right, so I have that force, and the other force, which is pushing her in this direction, is Fs. Right? And I want to know what is this force. That is, what is that maximum force that I can push on her with in order that she doesn't move. So I can do just like I did with the couch or the chair or whatever that is. I can say that the net force is equal to the mass times the acceleration. That's Newton's second law. So I can say F minus Fs. In this case, the acceleration is 0. F minus Fs is equal to 0. And so if I want to solve for the static frictional force, then I just say that the force is equal to the static frictional force. All right? If this doesn't make sense to you, that's okay. Because you can just say, well, this force is in this direction, so there has to be an equal and opposite force that's in the other direction. So I can just say this force, it has to equal this force because she's not moving. Right? That sort of makes sense intuitively, right? Like if you're playing tug of war and somebody's pulling with a certain force in one direction, and then somebody's pulling with a certain force in another direction, if they're not moving, then you assume that they're pulling with the same force, right? So it's sort of an intuitive thing. If the algebra doesn't make sense to you, don't sweat it. All right, so I can say then that this force is equal to my static frictional force. And then I'll go back and I'll say, well, my static frictional force is equal to my mu s, that's my coefficient of static friction, times my normal force. Now, what is my normal force to this person? What's her normal force? It's equal to what? Right, it's mass times gravity. It's just equal to her weight. So it's 70 kilograms times 10 meters per second squared. I'm going to go to the next page, okay, to give myself a little more space. So let me rewrite that. My static frictional force is equal to mu times the normal force. And the other thing that I wrote on the previous page was the force I'm looking for is equal to the static frictional force. So I can figure out now what the static frictional force is. If I look in that table on page 39 that you'll have on your quiz, the coefficient of static frictional force is 0.14. 0.14 times the normal force. The normal force is equal to the weight. Right. The coefficient of static friction is equal to 0.14. It's on page 39 in your book. And you'll have that table for the quiz, as well as all these equations. All these equations you'll have. All right? All right. So the normal force is equal to the weight. So then the normal force is equal to the mass times gravity. That's 70 kilograms times 10 meters per second squared. So her weight is 700 newtons. And so that's also equal to the normal force. So I can come back up here, take this, plug it in there. So I get 0.14 times 700. What's that? 98? Yeah, 98 newtons. I think that's right. Yeah. All right. So now I know that if I'm pushing on her, if I push with 98 newtons, that's not going to be enough to overcome the static frictional force. So she's going to be stationary. So that's my maximum force that I can push on her with. So the answer then is that the maximum force that you can push on her with, F, is going to be 98 newtons. What happens if I push with her, say, with 100 newtons? What's going to happen? She's going to move to the right. In that case, what type of friction is going to be at play? Are we going to be static friction or kinetic? What, Sam? Right, we're going to have kinetic friction at play. So when you exceed the static frictional force, that friction is no longer at play. Now you're going to have kinetic friction. All right? And is kinetic friction bigger or smaller than static friction? It's always smaller. Almost always. Right? Yeah, always. There are some homework problems like this in the assignment for this chapter. And then there are some other worked examples as well. Yeah. Right. She's not moving. Yeah. Is zero because your acceleration is zero? That's going to come up in just a second. It's not just that she's not moving, it's that she's not accelerating. Right. Right. That the acceleration is zero. Because from Newton's second law, F equals ma, that acceleration is zero. You with me on this? Is this okay? All right. If you have trouble, I know that some of you skills might not be so great, but if you have trouble with this, please come see me. I can help you, or if it's just overwhelming. The 700, I wanted to know her normal force. The normal force is just the force that's equal and opposite to the weight. All right, and so the 700 is just her weight. She has a mass of 70 kilograms. The acceleration due to gravity is 10, and so her weight is 700 newtons, and so that's also equal to the normal force. It was in the problem. Yeah. All right. No, 10 isn't given. 10 you need to know. That's the acceleration due to gravity. All right. So when objects fall within the Earth's gravitational field, that's the rate at which they fall. All right. I can include it. You want me to include it on the equation sheet? I think y'all know it, right? G is equal to 10. But I'll include it. All right. Now let's consider another part. Let's say part B of this. What force is required to make her move at constant velocity? What force is required to make her move at constant velocity? All right, so a couple questions you want to ask yourself. First, if she's moving at a constant velocity, what is her acceleration? It's zero, right. If she's moving at a constant velocity, that means that her speed isn't changing, so her acceleration is zero. Let me write that. At constant velocity, the acceleration is equal to zero. And because the acceleration is equal to zero, the net force is also equal to zero from Newton's second law. The other thing that you want to ask yourself is now that she's moving at a constant velocity, what type of friction is at play? Is it static or kinetic? Static or kinetic? I just heard ick. What is it? No, she's moving at it. She's now moving, right? So what's not static? Kinetic. Yeah, oh good. Kinetic. Yeah, so the friction that's at play now is kinetic friction. So also at constant velocity, kinetic friction is at play. It's the one that's actually acting on her. All right. So I want to know now, I have this skier. I'm pushing on her with a certain force, F. There's an equal and opposite force, Fk, and I want to know what that force is, F. All right, so F is going to equal Fk. That came about because she's not accelerating. All right, so I know that those two forces have to be equal but opposite. So F is equal to Fk. Fk is equal to mu k times the normal force. And then if I look at my table, the coefficient of kinetic friction is 0.1. Right, so this comes from page 39 in your book. And then the normal force we've already found, it's 700 newtons. This comes from M times G. In this class, the normal force will always be equal to the weight. All right. So the force required to keep her moving is 70 newtons. That's a pretty drastic difference, I think, that you can, and you're talking about something on snow, right, which is pretty easy to push. A person on skis on snow is pretty easy to push. But how many newtons difference was it between getting her to start moving and keeping her moving? How many newtons, roughly? Almost 30 newtons. So a newton is about a quarter pound, so a quarter of 30, what's that? About 7 pounds of force difference. That's a pretty significant difference between the static and the kinetic friction. And that's why you have these observed effects. Brakes or pushing furniture, which is quite a bit easier to push after you get it moving. All right. All right, let's see. No, the static frictional force, there is no static friction. When the person is moving, that friction is no longer relevant. All right. So there is no static friction. So whenever you encounter a problem that deals with friction, you need to ask yourself, well, is this person moving or is she not moving? And if she is moving, that's kinetic. If she's not moving, it's static friction. All right. Could y'all do this? If you had a problem pose something similar to this? All right, let's try a little practice problem. I'm not sure that you. All right. Let's say I have a box of 100 kilograms. How much force is required to move it? Right? How much force is required to get it moving? What's that initial force that I have to push? And let's say that the coefficient of kinetic friction is 0.1 and the coefficient of static friction is 0.2. They're usually not that big of a difference, but let's just say I have a box that's 100 kilograms. How much force is required to move it? I want you to try it on your own, okay? I'll give you a minute. You can work together, or if you have questions about where to start, please call me over. Remember, you're going to need to find the normal force. The normal force is equal to the weight. You'll need to find, what are we going to find, the static or the kinetic friction? Okay, I want to know the force where I'm just pushing it. Like just before it starts moving, what is that maximum force to push it? That's going to be the static frictional force. When you get an answer, let me know. Somebody have the normal force? Okay, 1,000. 1,000 newtons, yes, correct, 1,000 newtons. So the normal force is equal to the weight, and that's 1,000 newtons. So what's the amount of force required to get it moving? 200 newtons. Let me show you that. Our normal force is just equal to the weight. Normal force is equal to the weight. This is always going to be the case. It's equal to m times g. The normal force then is going to be equal to 100 kilograms times 10 meters per second squared, which is equal to 1,000 newtons. Now, I want to know what is the static frictional force. That's going to equal mu s times my normal force. That's 0.2 times 1,000 newtons. Oh, it's 200 newtons. That's what y'all said, right? 200? Yeah, 200 newtons. All right. So there are some more homework problems in the assignment for this chapter. But it'll be something similar to that for your exam. You just need to know to be able to identify when static and kinetic friction are acting. And you need to know how to calculate the static friction or the kinetic friction. You need to know how to use the table and find the appropriate values. And then also what is the normal force. There's a kind of a cool thing about friction. You might not know about this, but if you have two surfaces that come together, there's friction between those two surfaces. You know what causes the friction? What causes two surfaces to not stop with respect to one another? Okay, electricity is part of it, but there's a more macroscopic thing. Right, you're sort of getting ahead. If I have like Velcro, right? If I have Velcro that's rubbing against one another, what keeps it from moving very easily? You just get mechanical things, right, that grab onto one another, like ridges in the materials and stuff like that, that catch on one another, just like Velcro. Those little fibers in the Velcro will catch on one another, and they greatly increase the amount of friction. But, so if you take two surfaces, metal or wood or whatever, and you keep smoothing them and smoothing them and smoothing them, what happens to the friction? Does it increase or decrease? It decreases, right, because you get rid of those physical ridges, and they're a lot smoother, and they begin to move a lot more easily with respect to one another. But if you continue smoothing them and smoothing them and smoothing them, what do you think happens to the friction? It's going to start to increase. Can you think of a reason why, if I make my material so smooth that the amount of friction would begin to increase? Why, Ruth? Because of electricity, right? Because within the atoms of that material, you have these electrons and protons, and they get so close to one another that your electric forces begin to take over. And those mechanical forces aren't terribly important anymore. So they actually begin to stick on a molecular level or an atomic level, that the protons and electrons are bonded to one another. I think that's pretty cool, don't you think? Yeah, I think it's neat. All right. Let's move on. I'm going to look at a different force. So we had gravitational forces, frictional forces, and now I think this is the last force we'll look at. Yeah, tension. Use tension quite a bit, a variety of things. Let me tell you a joke first. Want to hear a good one? Listen, my wife said that this joke is not appropriate. So like before I tell you this joke, I need to have some assurance that, like if you're offended, that you'll forgive me and that you won't go to the dean and it'll be a big old mess. Can I have some assurance of that? Anybody offended by it? Joel? It's okay? Okay. All right, you ready? What's the difference between roast beef and pea soup? You say, I don't know. Yeah. Anybody can roast beef. Huh? You get it? You don't get anybody can roast beef. No one can pea soup. Are y'all offended? Okay, good. Don't get me in trouble. All right. Tension. All right, tension is a force carried by a rope or string. Or, et cetera. Something that's similar to that. In our body, what carries tension a lot? muscles and tendons and what have you. Tendons carry a force. And we'll look at how some of these tendons carry forces and how those forces can be very large. Carry a force exerted by muscles. To other parts of the body. I mean, y'all know more about tendons than I do, but it's my understanding that the tendons are attached to your muscles and then they're attached to your bones in some way. Is that correct? Yeah. Sorta. Okay. And then those muscles will exert a force, and then that'll pull whatever it is you want to move. That's a good simple understanding, right? Okay. All right. So tension is just a force carried by rope or string, and like for example tendons, and we'll have some problems in just a bit or later that deal with this. Let's just do a quick example. I think this is fairly self-explanatory, but let's say that I have a child in a basket. And they're 10 kilograms together, and they're suspended from a scale by a cord. So it's going to look something like this. I'll have, it's going to be my basket. It's my kid. They're attached to a cord to a scale. All right. I want to know what is the tension in the cord. In this case, the tension is going to equal what force? What is it, Lindsay? Okay, it is a static force, and that's a good point. There's no friction, but there is a static force, meaning that the forces aren't causing anything to move. All right, and that's actually very important. What is the net force on this object? It's not moving, not accelerating. What's the net force? It's 0, right. So that means that I have a force that's pulling up that's going to be equal and opposite to the force that's pulling down. What's the force that's pulling down? What's the force that's pulling down? Okay, right, 100 newtons. That's the mass of the object, the child, and the scale, times the gravitational acceleration. Right, so that's the force pulling down. What's the force pulling down? What? I'm sorry, what? Okay, yeah, it's going to be also 100 newtons. But what provides that force? Okay, the tension in the cord. So the cord is pulling up with an equal force of 100 newtons. So if I were to draw my force vectors, they're going to look like this. So I have one force that's pulling down. That's the gravitational force. That's the weight of the kid. And then I have another force that's pulling up. And this is going to be the tension in the cord. And because the acceleration is equal to 0, that means that the net force is equal to the mass times the acceleration. So the net force is equal to 0. The net force is going to be the tension minus the weight, and that's going to equal to 0. So I can say that the tension in the cord will equal the weight, which is equal to the mass, which is 10 kilograms, times 10 meters per second squared. That's G, is 100 newtons. All right? So that's how the tension in the cord is just 100 newtons. Let's do a little bit with vectors. This okay? Yeah? Again, there are some more homework problems that are similar to this, just dealing with Newton's second law. Let's look a little bit at vectors. You're not going to use vectors a whole lot in this class, but we're dealing with a lot of vector quantities. Vector quantities have what? We talked about vectors and scalars. Vector quantities have what? Remember, scalar quantities only had one certain thing. What was that? They only had a magnitude. And so we listed some scalar quantities, like time is a scalar quantity, mass is a scalar quantity, charge is also a scalar quantity. And then we also have vector quantities, like velocity and acceleration and forces are all vector quantities. So vector quantities not only have magnitude, but they also have direction, right? So vectors have a magnitude and a direction. And we're going to draw vectors in a certain way using what we call the graphical method. When we draw vectors with an arrow, the length of the arrow will equal the magnitude of our vector. That is, what's the quantity. And then the direction that it points will just equal the direction. All right? So this is called, we're going to call this the graphical method of representing vectors. All right, so let's say, for example, I draw an arrow representing a force. All right, and this arrow, I'm going to say, is 2 units long. All right, let's say you draw it at 2 inches. That means that my force is going to be 2 newtons, because I've drawn the arrow to be 2 units long. So here I'm letting 1 unit be a newton, and then another unit be another newton. So that my force is going to be 2 newtons, because my arrow is 2 units long. What if I were to draw an arrow like this? What would that force be? Here I've drawn it the same length, but I've drawn it in the opposite direction, not to the right, but to the left. And so my force is going to be, right, -2. So my force will be -2. And here, the negative denotes a left direction. All right. I could also draw, instead of drawing it 2 units long, I'll draw a vector like this. What would this force be? It would just be 1 newton, because it's just 1 unit long. 1 unit long. All right. We can use this to add up vectors. So let's say that I have 2 vectors, adding vectors in parallel, or parallel vectors. We've been doing that, right? When we're adding up the vectors, we have one vector going one direction and another vector going another direction, and then we say that the sum of them is 0. We've already been adding up these vectors just by taking one to be positive and one to be negative. Let's say that I have FA. My first vector is going to be +3 newtons, and then FB is going to be -1 newton. -1 newton. All right. I want to know what is FA plus FB. Right, so I can draw my vectors. I'll draw FA. It's going to be 3 units long. I'll draw it like this, 1, 2, 3. And then I'm going to draw FB. And FB, I'll draw in red, will look like this. It's 1 unit long, and it's in the opposite direction. So this is FB, and this is FA. And then I want to know what is the sum of those 2 vectors. When I take the sum of them, FA plus FB, I'm going to start at the beginning of FA, right here, and then I'll go to the end of FB, right here. So this vector is going to represent FA plus FB. How many units long is it? It's 2 units long. And we can see that because if we put in FA plus FB, which is -1, that's equal to 2. We've been doing that, adding parallel or anti-parallel vectors that are in the same direction or in the opposite directions with these sort of Newton's laws problem with the tension and the frictional forces and all that jazz. But this is just sort of solidifying it into a method. Now this becomes more useful. Honestly, vectors probably aren't going to be that useful to you, but whenever you're dealing with forces or any other sort of vector quantity, it's important to sort of have an idea of this idea of direction and magnitude. So it's important, I think. And it's important to just sort of think spatially about these things. Let's say that I have a vector, FA. FA is going to be 50 newtons to the right, and FB will be 25 newtons upward. So if I were to draw these vectors, now I want to know what FA plus FB equals. I'm going to use this method. I'm going to draw the first vector, FA. I'm going to break it into 2 pieces. So like this piece will be 25 newtons, and this piece will be 25 newtons. And now I'm going to draw FB. FB is going to be in this direction, and it's going to be exactly 1/2 the length of FA. So this is FB, and this is FA. Now, if I want to know FA plus FB, I'm going to start right here, and I'll draw it like that. So this vector will represent FA plus FB. All right? You can expect to see some questions on the quiz. I'll give you a little example question here in just a minute, just showing how to add up vectors graphically like this. Let's do another example. I think it's kind of fun, actually, when you deal with them, just sort of playing around with the arrows. Let's say that I have a vector, FA. Let's say that it's equal to 10 newtons at 45 degrees. And FE will be 20 newtons pointed upwards. All right? If I draw FA, FA is going to look like this. Actually, let me redraw that. So that this angle will be 45 degrees. All right. And then I'm going to draw FB, and it's going to be twice as big. This will be FB, and this will be FA. And then to take the net vector, the sum of these 2 vectors, FA plus FB, will look like this. All right, so this is equal to FA plus FB. Let me give you some questions you can try on your own. Let's say that I have 2 vectors. I'll call this FA. I'm just going to draw them for you. And I'll call this FB. I want you to tell me which of these options is correct. Give me just a minute, I'm going to write them. All right, which of these options is correct? If I want to know FA plus FB, Which of these is it? It's going to be A, B, C, or D. A, B, C, or D. Just take a second. I'm going to draw FA, and then you draw FB, starting from the end of FA, just like we did up here, and then connect the two. Which one is it going to be? A, B, C, or D? Okay. All right, I'll show you. So I draw FA first. This is FA. And then I'm going to draw FB. Now look, I have to move this vector FB around, but I can move it around however I want. So that's FB. So what's going to be the sum of FA plus FB? What do y'all think? Which one is it? It's going to be B, right? So I can start down at the bottom of FA and draw up to FB. So that's going to be the vector that's represented as option D. Oh. So I start down here and go up. And so this is FA plus FB, this vector. You want to do another? Do y'all follow what I'm doing? What's that? Which is that? Why'd you go up, down? Okay, when you're doing these vectors, you always want to, this is called delta. You always want to draw the first vector and then draw the second vector. Instead of one going to the tail of the other. Okay. A good way to think about it is, all right, if let's say that I start walking here at this point, and then I follow this vector, and then I follow this vector. Right. Remember displacement, the difference between displacement and distance? Displacement is a vector quantity, and it's only dependent upon your initial and final positions. So even though I've traveled from here to here, my displacement is only this amount. And my displacement goes from here to here. All right? So my displacement vector is always going to run from my initial position to my final position. If I was to draw it the other way, that would be from the final position to the initial position, and that wouldn't be correct. All right? Let's just do another example. I think some practice will help. All right, let's say that I have a vector FA here and FB here. And I want to know what the which of these vectors represents FA plus FB. Which one of these is it? Is it A, B, C, or D? What did y'all say? B's right. Yeah, B, that's what yeah, that's right. So if I draw FA, and then I draw FB, like this, the net vector, FA plus FB, is going to look like that. All right? I know this may seem like a sort of trivial thing to do, but it's actually fairly important. And when you get further in physics, like we'll do a lot of mathematical work with vectors, but this is a nice, simple way to understand vectors just from a conceptual standpoint. Y'all follow this? Y'all could do stuff like this? Likely to have a question like this on the test. I want to make sure that you can do it. Okay. Let's talk a little bit about some applications of this. We're going to look at forces and muscles. I don't know if y'all care, but I'm not trying to brag or anything, but I broke 1,000 miles on my bike this morning. Like, I'm not that I rode 1,000 miles this morning, but like I got this bike back in October, and I put 1,000 miles on it since I got it. So yeah, hey, thank you. Yeah, it's a. Have I ever shown you my bike? It's a recumbent bike. It's very nice. You ever have a recumbent? Yeah, it's like a lawn chair or a couch. No, did I tell you about this ride that I'm planning? No, I'm super excited about it. My birthday's coming up in May 27th. In case you want to know. And so I'm going to go on a tour, like a bike tour. I'm going to go from Baton Rouge, a little bit north of Baton Rouge, up to Jackson over like 3 days. And we're going to stay at, it's just me. I'm the only one going. But I'm going to stay like at B&Bs along the way. It'll be cool, right? Yeah, I'll bike. Well, my wife is going to bring me up north of Baton Rouge and let me off. And then they're going to come meet me. And she's just going to put me off like out in the wilderness. We sort of picked a spot up in the one of these wildlife management areas that goes up, and we'll go up to Natchez and then on up to Jackson. You ever ridden on the Natchez Trace, driven or biked? You have? You want to? It's very nice, I hear. I mean, I've driven on a car, but not on a bike. All right. So anyway, forces and muscles. It just reminded me because my legs are kind of sore. And that chair's not helping. Okay, so we have a number of different kind of muscles. Again, y'all probably know this better than I do. But we have flexor muscles. You could see some questions on your quiz just defining these, knowing what they do. These are muscles that cause bones to move closer together. We also have extensor muscles, which are closely related. These are muscles that cause bones to move further apart. Farther or further? What would be correct there? It doesn't matter to me. Farther apart. All right, so for example, like in your finger, I can make two motions with my finger. I can use muscles to move it in this direction, and I can use muscles to move it in this direction. What type of muscles move it in this direction? So flexor muscles, yes, because the bones are moving closer together. And what about here? Moving it from here to here. Extensor, yeah. So let me see if I can draw a picture. Oh, also tendons. We talked about tendons a little bit. These carry the force of the muscles. To a particular spot. All right, so for example, in your finger, you have these bones, lots of bones that are sort of jointed together. And then you have these muscles. This muscle is going to be called, this is the extensor muscle. And this muscle is called the flexor. And then they are connected with tendons. So you have these tendons that run along the finger that connect to the bone in different parts. Right. And so these tendons will convey the force that the muscles apply to your finger to make it move, or to your arms or your legs or whatever it is. There are other types of muscles. I'm sure there are a bunch of different kinds, but there are also sphincter muscles. It's kind of interesting. And sphincter muscles join back upon themselves to cause the constriction of an opening. I don't have examples of that, but I think y'all know what I mean, right? Okay. All right, so sphincter muscles. And again, these types of muscles, they're just attached to the bones, and they apply forces to those bones. We'll talk about this a little bit later in Chapter 5, talk about how we can calculate those forces and in terms of torques and rotation. Let's also look at traction systems. First, I have a little video. This is sort of semi-related. It's a video for an EMT, tech, where they're putting a person in traction. And there are a lot of different systems, like if you break a bone or whatever, particularly like if you break this bone. What is this? Femur? Or this one? This one's the femur, right? Yeah, like if you break this bone, then the muscles will cause the bones to sort of contract, or the muscles will contract and cause the bones to be misaligned. And so you have to put people in traction to apply a constant pressure or a constant force to those bones. And this is just a video with EMT techs applying traction to a mock-up patient. So a traction system, it's used for patients with broken bones, spinal injuries. For example, like the picture I showed you, to have a person, you can attach a weight to their head and put it on a pulley that have a certain weight, and that will apply a certain force to them. All right, that force is going to equal the weight of whatever mass you have. More commonly, you might have seen these, where if I have a leg, this is a leg, all right, with a broken femur, so I have a bone within here that has a break in it, and you want to apply pressure to it, you can set up this system of pulleys. It looks like this, where you attach a weight that has a certain mass, and it applies a force through this pulley that will apply a force to the traction system that will equal the weight of the mass, right? Right, so for traction systems, you just need to know that these forces are applied through these pulley systems in order to aid in healing of the bones. And again, that's something that y'all know about more than I do. So, but that's the end of Chapter 3. I think we'll wrap up there. And then we'll move into Chapter 4 next time, which is on energy and work and power. We'll talk about sort of the physical concepts of work and energy and how they're applied in our bodies and also sort of in physical systems. Any questions? If you have your proposal, bring it up to me, or just hand it to me, it's fine. Thank you, Shelley. Y'all have a good day, okay? I'll see y'all next, on Thursday. Okay, yeah, guys, if you don't have your quiz, come see me. Give me just a second.